now the ratio test, written on the board already here. It's a pretty simple test. You look at the ratio of the terms, an plus 1 over an. And you just take the absolute value of that. And then you take the limit as that goes to infinity. And it turns out that what you get will tell you what the series is doing. So if my ratio an plus 1 over an is less than 1, could be 0, that's fine, then the series is absolutely convergent. If my ratio is bigger than 1, or goes off to infinity, that happens sometimes, then the series is divergent. Well, that would be great, except it turns out that there is that case where the ratio is equal to 1. In that situation, this test tells you nothing, okay? And there are a lot of series that are in this situation. So that's why, though, this is an important test. You can test a lot of stuff with this, but you can't test everything with this, just like any other test. Because, of course, life couldn't be so easy, right? So let's do some examples. All right, I'm going to write it up in sort of shorthand at the top here, so that we keep it. Limit is convergent. So now what's nice about this test, by the way, is it works well for things with factorials, and it works well with things with powers of n, as well as like other n things. Let me do one like that, for example. Let's start with n times minus 4/9 to the n, for example. So this would be, it's very similar to, it's kind of like a geometric series, right? But it's got this extra n term, minus 1 to the n times 4 to the n over 9 to the n. If I write it that way, just to sort of look at it, you can see this ratio is going to be good because it's less than 1. But then there's this n term, right? N is growing fast. So you can't really use something like direct comparison very easily. And the limit comparison isn't going to help you there either. You're just going to get 0 or infinity. But what is really nice here is this ratio test works very well. So here, this is our an, or we can write it this way if we want. So an plus 1 over an in absolute value, well, I'll write it. This is my, all of this like this, right? And divided by an, these are almost always going to be fractions, so you can just go ahead and immediately write it as multiplying by the reciprocal. Okay. Well, the absolute value kills the minus 1, right? So we don't have to worry about that. This guy, those guys cancel. You have a minus 1. The absolute value will kill it. This is what I'm saying. This is why it's nice for these ratios. You can cross out a lot of stuff. It simplifies fast. So without the, so once we apply the absolute value to kill that minus 1, what I really have here is n plus 1 over n times 4 over 9. Right, so all these canceled out. my n stays, my n plus 1 stays. I have a value of 4 and one value of 9. So we want to take the limit of this. This part just goes to 1, right? And this just 4 9. If I want, I can write it carefully. Right? And then I can multiply top and bottom by 1 over n. I trust you guys recognize that this goes to 1 at this point, so we can just write 4 9. 4 9 is less than 1, so this series converges. Absolutely, in fact. Ratio test will always tell you about the absolute convergence. So if it converges by the ratio test, it means it converges absolutely. Okay. If there's no negatives, then fine. The absolute values don't do anything. Okay. So let me do 1 or 2 more to show you what happens when things go bad. Better, less bad. And then we can do a whole lot of interesting examples with this test as well. So, this one, let's do this one. This one also has a minus 1 in it. Okay. So, I'm just going to write down an plus 1 over an here. Yeah, I'm kind of running out of space with that thing. Let me move it up next time. And then here I'm going to have n to the 4th and minus 1 to the n minus 1 and 2 to the n. Okay, so here we have a little bit less stuff to cancel. I can't cancel these out, but I can cancel out the 2 to the n and most of those, right? But they'll get killed by the absolute value anyway. So what I really have here is 2n to the 4th over n plus 1 to the 4th. So maybe this limit we can be a little sloppy, or you could do a couple ways, right? You could put this all together under the 4. It might just be easier to write out what n to the 4th is, but you don't really need to know, right? It's 4, 6, 4, whatever. I'm going to write plus dot, dot, dot. Because I don't care what those terms are. I'm taking n to infinity. When I take n to infinity, dividing these guys by this, what I have is limit as n goes to infinity of 2 over 1 plus all these other terms, whatever they are, they've got n stuff in the bottom, so all those go to 0. This is greater than 1. This diverges. Okay? And sort of just to kind of get some feeling for them, you can, as you do more ratio test problems, you'll see this. We can look at what everything's doing. This 2 to the n is going to go up really fast. N to the 4th goes up fast, but it doesn't go up as fast as the exponential. So if you can think about that, that will kind of give you an idea. But writing that down isn't going to give me a proof or a proper explanation. I really want to see you apply one of these tests. Okay, but just from an intuition point of view, it's kind of nice to think about, oh, what do I expect this to do? Of course, you won't know for all of them, but the more of them you do, you'll get some idea. So that was a convergence, that was a divergence. I gotta, of course, use one that doesn't tell you anything. So you see what works with how that works. So here's one. Okay. Now I'm just gonna tell you, for the purposes of don't waste your time, whenever you have a rational function, the ratio test is going to fail, okay? Because it's going to end up being 1. So by fail, I mean it's going to be an inconclusive test. You're going to do something else. So, but here, just to show you how it works, or why that happens, this would be 3n plus 1 plus 2 over 4n plus 1 squared minus 5, and then divide, multiply top and bottom by this. So we have to multiply this thing out. I mean, I put the absolute values, but honestly, these are all positive terms, so I don't need the absolute values. Okay. So what do I have? I have 4n squared plus 2n plus 1 minus 5 times 3n plus 2, and on the top, I have 3 times n squared plus 2n plus 1 plus 2 times 4n squared minus 5. All right, well, because I couldn't have picked a simpler example, right? All right, I'll write it out. So this would be minus 1. And this would be 3n squared plus 6n plus 3 plus 2, so plus 5. So, do we really need them all? No, but let's just be careful. Okay, we'll be careful, go through at least some of these. Wait, I can't do it like that. I'll just have my turns. This one minus 15n squared plus 24n cubed minus 30n plus 20n squared minus 25, whatever. And essentially, it really doesn't matter what all these lower ones are. The only important one is the leading term, okay? I'm just writing it out so that you see, for one example, what's going to happen. But honestly, do you need to write all this crap out? No. Because you can see what's going to happen when I take this limit. I'm going to move these chairs. All this stuff is going to go to 0. Okay? So if I do the limit as n goes to infinity of this, what am I doing? I'm multiplying top and bottom by n to the 4th. Right? Because, wait a minute. What do I do? Something's wrong here. Great. There goes that video. All right, we can fix it. It's supposed to be n to the 3rd because this one doesn't have a square. See? So this should be 3n plus 5. That's not going to go to 1. Yeah. See? There's no square here. When I wrote it there, I wrote a square. So this is actually going to be, let me just fix it. The bottom part's fine. Actually, it's not because it's cute. All right, I'm going to redo it. How about that? How many people notice that when I did it? That's the question I want to know. Because I sure didn't notice that. So this is going to be 12, 12 minus 15 and plus 20 n squared minus 25. And then this other one is going to be, and you see that those are the perils of trying to illustrate something without doing it very carefully, right? Because I knew it was supposed to be the same power, so I wrote it the same power. Okay. If I had been paying better attention, I would have noticed my mistake earlier. All right. Now, if I take the limit of this, at least now I have the right powers, the powers that are correct. Divide everything by 1 over n cubed. I'm going to have 12 plus a bunch of stuff on the top and on the bottom. So I have 1. As I promised you, it would be 1. It is, in fact, 1. And it should be the power, the total number of powers, right? Because you're multiplying. This is going to happen for one of these rational functions, regardless of whether your underlying series converges or diverges. You can compare ratio test with 1 over n and ratio test with 1 over n squared. You're going to get 1 with both of them. So that's a cute exercise, a lot shorter than this. But this just goes to show you the same thing happens with something more difficult or more numbers. This is essentially going to diverge, okay, because it's going to behave like 1 over n squared. And if I wanted to do this, I would just do it with limit comparison. I would limit comparison it with 1 over n, right? It's n over n squared, so it should be limit comparison with 1 over n.